Good afternoon, everyone. My name is Vikas Rao, and I'm excited to present our work on rectification of integer arithmetic circuits using computer algebra techniques at this prestigious ICCD conference. Let me quickly give you an overview of what the problem statement and objective is. Let's say we are given this circuit, right? So this is a 3-bit modulo multiplier design. As you can see, I've marked gates F26 and F27 in red, meaning this is a faulty circuit where these were supposed to be AND gates and they have been replaced with XOR gates. The kind of questions that we want to ask is, does this circuit actually implement the specification? Of course, verification, you can perform verification and verification will deem whether the circuit implements the specification or not. So once verification deems that the circuit is faulty, next question that we want to ask is, can we rectify this circuit to match the specification? So when I say rectify, can we change some logic functions somewhere in the circuit and the patched circuit, can it match the specification? Of course, trivially, you can always synthesize the whole output bits and the circuit will match specification, right? So can we do it at internal nets? So let's say we pick the nets R3 and RR3, right? So if we put a black box here, can I implement some kind of logic in this black box such that the patched circuit matches the specification? So our work essentially answers this question. So the first part is whether these two nets, they admit rectification. If so, what should be the rectification function? And these are the kind of questions that we want to answer here. So state of the art, the contemporary techniques, right? So they implement this as a QBF. So in this case, this cone here, RF, essentially is the black box. So the question asked is whether does there exist some kind of RF, an implementation, such that for all primary inputs, the spec matches the implementation. Right? So, and traditionally QBF has been solved using partial equivalence checking or Craig interpolation, or most recently incremental SAT solving. Right? However, all these techniques are infeasible for arithmetic circuits. So our approach, on the other hand, uses an algebraic model. We formulate this problem over fields. Even though we are working over integer arithmetic circuits, we formulate it over fields because most of the algebraic geometry results are well defined over fields as opposed to integer rings. However, there has been work which is done where verification of integer arithmetic circuits is performed in Q. Verification, however, is just a decision procedure, whereas our work involves quantification. So we compute, the functions which we obtain are essentially in higher fields, which is in Q. Right? So these functions, right? So we are interested in the zeros of these functions. See, these zeros might correspond to onset or offset or union of offset and DC set and onset and DC set and so on. So this zero set of a polynomial is known as variety. Right. So let me quickly give you what kind of functions we come across. Right. So as you can see, this polynomial here has fraction coefficients and also some integer coefficients. Right. This, of course, cannot be synthesized. Now we are interested in functions which look something like this. As you can see here over mod 2, this logic here is synthesizable because this evaluates only to zeros and one. Right. So if you actually look at the functional evaluation of both these polynomials, there are some places where f evaluates to 0, and the rest of the places it evaluates to some non-zero value. Right. So we are interested in f synth, which retains the zeros of the polynomial f and evaluates to 1, where f evaluates to non-zero values. So this was one of the main challenges that we faced, and in the paper we have in detail described the theory behind arriving from a polynomial which looks like f to a polynomial which looks like f synth. Right. So let me just quickly run you through an example. Right. So let's say we are given a specification of an integer multiplier circuit. So here SI is a 2n-bit output and AI and BI are n-bit inputs. Right. So given a circuit and this specification, for the gate level circuit, we model the gates as polynomials as shown in this relation. Right. So for example, an XOR gate, V XOR W is represented as V plus W minus 2VW. So these polynomials together form something called as an ideal, which is represented here as J. We also need another ideal called J0, which is basically the ideal of vanishing polynomials. This basically maintains the idempotency of the circuit. Right. So then we say J plus J0, the ideal together, it actually models the functionality of the circuit. So next is to perform rectification check, right? So here, let's assume that in our work, we assume that the nets are actually given or found through some kind of heuristic, right? So let's say we are given this circuits R3 and RR3, right? So we assign 0, 0 to these nets, and then we perform what is known as a polynomial division, right? So we take the specification F, reduce it by the ideal J1 plus J0, and we obtain a remainder M1. So similarly, we obtain multiple other remainders where we assign these two nets to 0, 1, 1, 0, and 1, 1. And we get REM2, REM3, and REM4 respectively, right? So this is what mathematically, these are what the equations look like. So as you can see here, REM1, REM2, REM3, and REM4, we get a remainder in terms of primary inputs with some integer coefficients, right? So we say that rectification is possible if and only if the product of these remainders reduced by the idempotency ideal, it gives us a 0. Right. So what does this mean? Right. So it means that the nets actually admit rectification. So once these nets admit rectification, we need to compute rectification functions. So we have presented two different approaches here. So the first one is a greedy approach where we look at the variety of these remainders that are generated, and we tried to assign the points towards the offset of the target functions when need as much as we can, and only push the points into the onset of the function when it is necessary. So this is done according to an order, right? So here, all the don't care points are essentially pushed towards the offset of the function based on this order. So another approach is basically evaluates a subset of DC points where we look where we compute pairwise intersection of don't care conditions across the targets. So this is the overall approach. So we take the specification, the faulty circuit, and we are given a set of targets, and we perform verification using Revesi or Amulet. These are basically the available open source algebra tools. Then we check whether these nets admit rectification. This is done using a singular or Amulet again. After that, we compute to compute a rectification function. If the nets admit rectification, to compute a rectification function, we perform this union, intersection, and set difference of these remainders using our in-house Python and open source singular algebra tool. Right. So, and in the end, once we have all these functions, we synthesize the logic using ABC and sys. So here are the experimental results. We were able to perform rectification up to successfully up to 32-bit multipliers. Of course, there are a lot of bottlenecks involved right now with respect to computing the reduced Grobner basis, or in fact, even working of Revesi and Amulet. So we are working towards improving these results. Thank you for your time. Let me know if you have any questions.